Equilibrium and torque, day 3. Here we have a sledgehammer, as pictured. It's a large hammer used for doing heavy-duty jobs around the house, like busting up concrete or pounding in big posts into the ground and so forth. Upon further review, the word sledgehammer is one word, not two. Sorry about that. But anyways, back to the actual problem. Like all these torque problems, what you want to do, or what I suggest you do, is simplify the object as a little stick figure, your free body force diagram. That red line there represents the sledgehammer laying sideways on the ground. And then apply all your force vector arrows. There is a 90 Newton weight, the sledge part, the business end of the sledgehammer. And like all torque problems, you want to put the weight, that entire weight, at the center of gravity of that part of the object, which would be 5 centimeters from the end of the sledgehammer. So this would be the 90 Newton weight, 5 centimeters from the end of the sledgehammer at that end. The 12 Newton weight, the weight of the handle, once again is placed at the center of gravity of the handle. Since the handle is 80 centimeters long, that weight vector, the 12 Newton vector, would be 40 centimeters from the other end, the end of the handle, and there would be 45 centimeters between these two weight vectors. But before I label that, these are the only two weights, the actual weights of this sledgehammer. And the principle, once again, is to find the center of gravity of the system. We know the center of gravity of the two parts here, but where's the center of gravity of the system? Well, somewhere between those two parts, closer to where the heavier weight is, the 90 newtons. And the way you want to find that is by balancing this object with an upper force, a force pointing upward, of 102 newtons to balance off the 102 newtons downward. The question is, where does that force, where is it going to be applied? So we have three spots here. We have three forces. But this upward 102 Newton force will balance it out. Let me label these points, A, B, C. Now we only have three forces, unlike the previous problems which had four. And I really don't know the distances between the forces, the downward force and that upward force. However, I do know that from A to C is 45 centimeters. Let me label that. Because the whole sledgehammer is 90 centimeters long. Once again, like our other problems, you want to pick any one of these three spots. The worst spot to pick here is point B because you don't know its location. You know the location of the other two spots, A and C, so it doesn't really matter which of those two spots you pick as your reference point for calculating the balanced torques. So let's pick point A as my reference point to calculate my torques. I want my clockwise torque equal to my counterclockwise torque. So if I pick point A as a fixed point that's not going to move, pinned down, and if I let things rotate around there like the hand of a clock, if point C goes down, it will rotate clockwise around point A, like a planet rotating around a sun. If point A is the sun, the fixed object, point C will rotate clockwise. So that's going to be my clockwise torque. That will be then the force of 12 newtons times its distance from point A, 45 centimeters, times the sine of 90, which we will not need to write down because the sine of 90 is 1, equals then the counterclockwise producing torque, or force, which is 102 newtons, times the distance from point A, which we don't know. I'm going to call that D. I'll label that right here. That is a D, the distance between points A and B. All right, so that's D. And I go to my calculator. D comes out to be 5.3 centimeters. And that's the answer to the problem. That's the center of gravity of this system. 5.3 centimeters, which is just outside the heavy weight, just barely on the handle. 0.3 centimeters or 3 millimeters away from where they connect together. So if you want to put that in words, And actually, the actual center of gravity is actually inside that handle, inside the wood, in the cross-sectional area of the wood. But just locating where it is in reference to the length of this sledgehammer is good enough. So that would be 5.3 centimeters away from the center of gravity of the weight. 5.3 centimeters from the CG of the heavy weight. A properly labeled diagram is very important here. Here we have a traffic signal suspended by a cable in the middle of the street. On the left-hand side is a post by the side of the road. The key object here is this beam, or this boom, that's angled, and I've highlighted it in red, that's angled up and then holds the weight, the 400-pound traffic signal, in the middle of the road. We want to find the tension, the force in that horizontal rope at the top, and the magnitude of the force where the beam connects to the side post here. I just highlighted that in blue. I'm going to call that point A. That's where this angled beam or boom attaches to the vertical post. Alright, so this one's going to be a little bit more complicated and involved, as you can imagine. But once again, the principle is the same. I want to draw a simplified diagram. This would be the beam or the boom, simplified instead of all thick and shaded. That's that angled beam. Here's the free body force diagram. We have one rope pulling this way. I'm going to call that T1, which is what I'm trying to find in part A. Then I have another cable pulling down, but I already know that that's 400 pounds of weight or tension, and we can do this in pounds. That's a force. That's pulling straight down. Now I also know that the beam itself weighs 100 pounds, and it's a uniform beam. So once again, the idea is you put the entire weight, 100 pounds, of the object at its center of gravity, which would be geometrically in the center here, straight down. That's going to be 100 pounds. But I don't know how long this beam is yet, but if you look at the diagram on the left, and let me highlight this in blue. If I look at this triangle right here in blue, I'll go over it a couple times, and I just went over some of the numbers there, but that blue triangle, the hypotenuse is the beam. And I know the two legs. I have 10 squared plus 12 squared equals L squared, the length of this boom. Solving that using the Pythagorean theorem comes out to be 16 feet. That's the length of the actual boom. What also will be important is this angle up here, call that theta, in the upper right part of that blue triangle. And I can figure that out using tangent. Tangent of theta equals 10 over 12, opposite over hypotenuse. That gives me a theta of 40 degrees. Alright, so if I go back up to my simplified diagram over here on the right now, if I can squeeze that in, that's 40 degrees up there. That's going to be important. That means that this is 50 degrees because those two angles are complementary. And then therefore, this angle over here is also 50 degrees because that's corresponding to the angle at the top when two parallel lines, the two weight vectors, are cut by the transversal, which is the red boom. Now, one more thing, and the hardest part about these problems is down here at point A. So this spot right here is point A. What's happening there in all these problems that you get when you have booms like this, there's going to be a crane problem in the homework, and maybe some other variations of ladders and things like that. But when it is connected to something on the ground or on a pole like this, there will be two components to the force that act at that location. There's going to be a force that acts upward here. I'm going to call that F sub Y, vertical. And there's going to be a component that acts horizontally. Call that F sub X, like we've done before. So F sub x and F sub y are components of an actual force F, which we can find after we have the components. We can put those together by the Pythagorean theorem to figure out the actual force F at that location. But let's start off with the easy stuff. I know that right away F sub y is 500 pounds of force because we have to have translational equilibrium. The up and down forces have to match. We have 500 pounds down, 400 plus 100. So F sub y must be 500 pounds. So it feels like, or it looks like maybe we're halfway home, which we're not because that's the easy one. F sub x is a little bit more difficult. It's going to be equal to t sub 1, but we don't know t sub 1 or F sub x yet. So the way we're going to do that is we're going to use the concept of balanced torques. This down here on the left here is point A once again. I'm going to calculate my torque with respect to that spot. So I'm using point A as my reference point to calculate torque. And I'm going to have the same thing as before. I want my clockwise torque equal to my counterclockwise torque. Alright, so if I look at point A, alright, the weight vectors, the 100 pounds and the 400 pounds, if you were to cut that cable to the top, the 12-foot cable T1, and point A stays fixed and stuck to the wall, the whole thing would rotate clockwise based on both those two, the 100 pounds and the 400 pounds. So those are creating clockwise torque. So here's where it gets interesting, however. If I write that down, what I have is the force times the distance. Oh, I didn't figure out the distance yet. I did. The total length of that beam is 16 feet. Therefore, that 100-pound force is 8 feet from point A. So 8 feet there. It's split into two 8-foot sections because the center is then the midpoint of the 16-foot beam. So if I then calculate the torques with respect to point A, I'm going to have my force, which is 100-pound force, times the distance, 8 meters, from point A. Now, though, times the sine of 50, because it's not at a right angle to the beam. It's at a 50-degree angle as labeled. Plus the 400 times the distance of 16 meters times the sine of 50 as well, the angle it makes with the beam, equals then the counterclockwise torque, which is produced only by T1. Remember, from point A, F sub x and F sub y are not creating any torque at all because they have no distance from point A. T1 is pulling and trying to make the whole thing rotate counterclockwise to balance out the torques. I'm a little out of space here, but it will essentially be T1 times the distance of 16 times the sine of 40 degrees. So I have one big long equation there. But if I do the math here, I'm going to take the 100 times 8, which is 800, times the sine of 50, that is 613 Newton meters, but actually it's not Newton meters, it's foot-pounds. I'm doing everything in English here. I didn't make any conversions, which makes it, well, it's not a difficult, it's more difficult to actually do all the conversions. We don't need to convert. Everything will be in feet here, and everything will be in pounds as far as our forces and our distances, which is perfectly okay. But anyways, we get 313 foot-pounds plus 4,900 foot-pounds equals T1 times 16 times the sine of 40, which is 10.3 T1. 10.3 T1. Sorry, I'm a little out of space here. Let me adjust this. I rewrote everything in blue here. Maybe it's a little easier to see now. It came out to be 613 foot-pounds plus 4,900 foot-pounds equals 10.3 T1. Add those two numbers together, you get 5513 equals 10.3 T1. Divide by 10.3. T1 comes out to be, I'm going to round off to 2 sig figs here, 540 pounds of tension, force, in that cable. That automatically means that F sub x is 540 pounds because those are the only two sideways acting forces, and once again we need to have F net equals 0 sideways in addition to the up and down. So I have my F sub x, and I know F sub y. But this right here, T sub 1, is the answer to part A. Now I need to find the actual force F that's acting at the hinge. Well, I'll do it in red. If I have one force, we just found the F sub x is 540 pounds pushing out on the beam, keeping it from pushing into the pole, and then a support force of I think it was 500 pounds, because that was the 100 plus the 400. Those are both in pounds. Therefore, the overall resulting force, F, is the hypotenuse there. That diagram will suffice as far as I'm concerned, showing me the component diagram put back together to find F. If you want to write it all out, 540 squared plus 500 squared equals F squared. F comes out to be 740 pounds to 2 sig figs. That's my force at point A. And you could figure out the angle as well if you wanted to. You don't have to here because it said just find the magnitude of the force acting at that pin or at that point A, and that's the answer. So good luck with these. We'll see you in class.